But anyway, let's start with, here's what we did. We had a little preview of this topic, and what we had was population growth problems. And really quickly, I just want to say that we kind of had that's right, we had an English sentence that we wrote as a mathematical sentence. And that was a population growth model. When you solve this differential equation, the answer is C e to the kt. And we proved that the other day. We separated and integrated and kind of went through that actually. And so then some of these word problems turn into very algebraic problems. In fact, I did one example last week where that was just, when you end up using this model, it's very algebraic. You've already done the differential equation calculus part of this by deriving this model. We also had temperature model that looked like this, dt dt. This is Newton's law of cooling. It looked like that, and the answer to that was when m is a constant, m is the temperature of the surrounding medium, and when m is a constant, the solution to the dE is this. So that's a popular one. I did not do any examples of that. So we've got temperature, population growth, but this also works with money growth or radioactive decay. This is good, exponential growth and decay. This is temperature problems. And then we had these interesting mixing tank problems, mixing solutions, solution mixtures problems, and those are fun. But I want to start with this one. There's one good one now. Here's a population problem on the back here, on the back of this paper called number 3. And I'm not going to write the whole problem down, but I am going to kind of read it and write down the important information. This is a good problem. This is kind of sophisticated. So on the back of these notes I gave you the other day, anybody need a copy of these notes that I gave you the other day? I got a couple extra. And on the back is some good problems. And I want to do this number 3. That's all right. And I want you to help me. I don't want to totally do it. You can help me. It says on an island that had no cats, the mouse population doubled during the years 1970 to 1975. Okay. Reaching 30,000. Wow, 30,000 mice on this island. At that time, the islanders imported one really mean cat, which thereafter killed 4,000 mice per year. Wow. So that describes a situation. And I would say we should be able to write a differential equation for that. But what, do you have a thought there? See, there's something more going on than just good old population growth, right? What happened? There is population growth. The mice are growing. Their population is growing, but the cat comes in and starts killing them. So then we have something else happen. So that, well, the mice are still growing, and then there's this death rate involved thanks to the cat. But my point is, there's growth at first, and then the cat comes into play. I want to say that's a piecewise. Thank you. This is a piecewise situation. And the differential equation, I think, would be, now this is, I think for those first 5 years is what it said, it's good old normal population growth, which I would suggest is this, you guys. That's the DE. And I think that works for T between 0 and 5. From 1970 to 1975, I guess we'll call 1970 0. Hey, welcome. Watch out for my little tripod there, but you can sit there, I think, or there, or way ahead. Yeah, good old population growth for the first 5 years. And by the way, now, if I want to solve this DE, look, you guys, when I solve it, it's going to be a piecewise solution. And to tell you the truth, I know the solution to the first part because, like I said, we've solved that DE a million times. And so it's the solution to the first part is going to be this. For t between 0 and 5 years. By the way, we're working on number 3 on the back of this sheet. It's a good little population problem. Number 3 on the back of this sheet I gave you the other day. Okay. Here, the tricky part is, and students and I have argued about this for years. Maybe I'll cut through the arguing and tell you the answer, but setting up this, I mean, you know, what's going on after 1975 is this cat comes in here and starts killing some mice. But the mice still have their good old growth. Now, I feel like the mice have they're still doing their thing, you know, and they got population growth. But now this cat comes in and kills 4,000 mice per year. I think I got population growth, and then I got to subtract sort of a death rate. And what do you think that would be? He's killing 4,000 mice per year. So that's good. You guys want to, this is what I've argued about in the past. You just said, let's put 4,000 T, because it's 4,000 per year, so then you want to multiply by the number of years to get the mice. But hold on. What we're setting up right here is actually the rate of growth. And the units on this is what helps you sometimes in differential equations, is to think about the units. The units on this are mice per year. So in the DE, I don't think I want to put the T on there. I mean, I think I have the growth rate, and I think I want to kill 4,000 mice per year, and I think that would just be a minus 4,000, because that's a 4,000 mice per year. It's a rate. I've also argued that perhaps it should be, never mind. I think over the years, I've done this problem. I think there's been arguments that maybe it should be this. The growth rate is proportional to the population minus 4,000. But, I don't know, that's kind of subtle, and anyway, I think I've reached that conclusion. I think that's better. So we have a piecewise differential equation. We already solved the top piece just because we know that's the answer. To solve this bottom piece, let's do it. Let's see here. It's a differential equation. dP dt equals Kp minus 4,000. You know what? I think I want to move the Kp over. Minus Kp equals negative 4,000. I want to use my integrating factor methods. We need this in chapter 3 a lot. I want to find the integrating factor. The integrating factor is e to the negative kt. Do you agree with that? It's the integral of that negative k. I multiply through by the integrating factor. After I multiply through by the integrating factor, the left-hand side becomes the derivative of the e to the negative kt times p, the population of mice, equals negative 4,000. Now you integrate. Oh, I forgot to multiply through. Thank you very much. You multiply through by the e to the negative kt. I forgot to multiply through. It comes over here. Yes, sir. Yes, sir. You multiply through by the e to the negative kt. This left-hand side becomes this product rule. The right-hand side is that, and now you integrate. Integrate both sides of this DE. We practiced this for 2 weeks, few weeks. Here we go, e to the negative kt times p. Hey, when you integrate this, it spits out the constant negative k. Actually, it spits out a negative 1 over k when you integrate that. You do a little u substitution, it spits out a negative 1 over k. That'll be 4,000 over k. The negative signs canceled. E to the negative kt. I think I did that right. Plus c. Excuse me a second. There was a C in the top piece of this piecewise DE. So I'm going to call him C1, and I'll call this one C2. Hey, we're almost done. Divide by this e to the negative kt, and the population is 4,000 over k plus C2 e to the kt. Yeah, that's good. That's good. That's my answer. Now what I've done, I guess, I've solved this differential equation sort of in general. I haven't put anything specific in here yet, except the 4,000 death rate. But this is it. This is our piecewise solution to this scenario, which is a population of mice that would be growing out of control, but maybe this cat is keeping it under control. I really don't know yet. I got some questions about the future here. Did we have an initial condition on this problem? At time 0, was there an initial population? I hope so.
15,000.
Yeah, good. It was worded a little funny. What it says is that from 1970, which was time 0, 1970 is time 0. It said from 1970 to 75, it doubled to 30,000, which means it must have started at 15,000, right? It was a little subtle there, but good. Well, of course, you can use that probably to find C, that first C. In fact, maybe you recall, I said this last week, in these population problems, that C is always the initial population. The initial population. So it's 15,000. You can plug in the numbers and watch it happen, but this is always the initial population. By the way, that's not true in some of our other models. This C is not the initial temperature. It's not. Because there's other factors involved. There's other numbers involved. Right. But in that it is. Okay, all right. So I'm going to try to fill this in a little more specifically then. That's 15,000. I wish I knew that K. I wonder how I can find K. Do I have another piece of information? I had this initial condition. Oh, I did have that. Thank you. In 5 years, yes, in 5 years, the population doubled to 30,000. I think I can use that to find K. Yes. I'll do that right here. What I have is my model over there. What I'm going to do is I'm going to plug 30,000 in for P. 15,000 is already in there for C. E to the K times T. And T is 5 years. In 5 years, you get 30,000. And now you solve for K. This is algebra. Divide by 15,000, you get 2. That's your doubling population. Take the natural log of both sides, you divide by 5, and here's K. It's the natural log of 2 divided by 5. Somebody decimalize that for me.
0.139.
And again, in these problems, in these population, all these exponential growth and decay kind of problems, I never want to round that K too much. Rounding it too much will round your answer too much. So when I ask for K, I really want all 30,000 decimals, please.
0.138629431. Approximately.
That's all you can give me? No, that's good enough.
That's all
Yeah, that's good enough. Yeah, 9 or 10 decimals is what your calculator will do. That's good enough. Or the truth is, I can just kind of leave it exact like this. I'll just carry around this K if you don't mind. But there it is. I wanted to see what it was. Okay, so I'm going to just put this in my little equation here. The natural log of 2 over 5 is my K times T. I mean, it's shorter to write that than it is all those decimals, so I'm writing that. You know, here's something else. In the second piece of the equation, there's K, and maybe you've already thought this out, maybe you didn't think this out yet, but it's the same K. I don't have enough information to attack this problem if it was a different k. But I'm going to assume it's the same k, because k has to do with the rate at which the mice are sort of doing their thing. It's kind of, it's the same k. Even though the cat is now killing 4,000 mice per year, the growth rate is still the same k, I believe. So that means I'm darn close to the answer here. This is, yeah, this second solution is 4,000 over k, which is the natural log of 2 over 5. You could simplify that a little bit. Plus, I don't know this C2 though. I don't know C2. And then I have e to the log 2 over 5 times t. I mean, I almost have this thing solved. I need, what do I need to finish this problem, you guys? I need C2. And how do you find C2 in a piecewise situation? Yeah, what did you just say? Yes, set them equal to each other at the place where they change at 5. Yes, set them equal to each other at 5. Technically what you're doing is you're making this solution continuous. Technically by taking the limit as t approaches 5 from the left and the t approaches 5 from the right. What that amounts to is setting them equal to each other at 5. Yes, yes. And you can get C2. And you've solved this DE. I'm going to do that. When t is 5, I'm going to plug it into that top equation. And you know what I'm going to get? I'm going to get the population when t is 5. I mean, I could do the math there, but I already know it's 30,000. Yeah. When t is 5, I get 30,000 mice. I'm going to set that equal to this thing, and I can find C2. What I have here is 4,000 over this. I'm going to flip that 5 up. I'm going to call that 20,000 over log 2. At some point, I will decimalize this in order to get C2. And then plugging in a 5 there. Is that what I'm doing? Watch this. The 5's cancel. You have e to the log 2. E and log cancel. You have a 2. Now, it doesn't always work out that nice. But that worked out nice. Anyway, I still, like I said, I would like you to help me decimalize and give me, I want a decimalized answer for C2. You know, I like to keep my math pure and exact, but when it is a word problem, at some point decimalizing is okay. Again, I'm worried about rounding this. I don't want to like rounding this guy too much, but finding a rounded off C2 is fine here. So help me out. Divide that number, subtract it, and then you'll have to divide by 2, I guess. And C2 is
573. 0.04959.
049. Okay, we'll say 0.5 maybe.
Was that right?
Yeah, that's right.
Okay.
So we are finished, and I could rewrite this whole solution. This is the solution. To tell you the truth, though, with the magic of the whiteboard, I can just come over here and erase that little C2 and put that answer in there and save myself a little writing. 573.05 e to the, this is it. This is the solution to the piecewise differential equation. You know, the question said this, part A, what is the number of mice on the island at year T? Well, guess what? I mean, that's kind of a confusing question to students sometimes. The number of mice on the island at year T. Well, that's any year T. You know what that is? That's this answer. This is the number of mice on the island at any year T. Thank you. It's the function. It's the solution to the DE. Then I do ask how many mice will be on the island in 2007. Well, what is 2007?
T equals 37. 7 bigger than 5.
In 2007, I mean, everything started at 1970, T was 0. So you're saying T is 37. Okay, you know, here's the issue with a piecewise function. Should you plug 37 into the top piece or the bottom piece? Well, of course, right. This is only good for the first 5 years. After 5 years, you're using the bottom piece here. Yeah, we could plug in 37 years and see what happens. I don't think this cat's doing that great a job. Because this is positive. I mean, this could be, I don't know. I make up these problems. I really have no idea what's going on. You know, maybe the cat's doing a great job and we actually end up with negative number of mice, which ain't too realistic, but that's how great of a job he did. Or maybe he's doing a medium job, we end up with a medium amount of mice. Or maybe he's not doing a good job and this mice population is still exploding like crazy, maybe. It probably is exploding. But I want to plug in a 37 into this bottom piece of this function and see what the answer is, I guess. P of 37 would be that 20,000 over ln2 plus that 573.05 e to the ln2 over 5 times 37. Sometimes students have a little issue with their calculator here. Make sure you do this exponent, then you e it, then you multiply it, then you add it.
Can't we just make that, cancel out the e and the ln, it's 2 raised 37 over 5?
Yes.
Yes. So it's just
But I'm not sure how much greater that is to the 37 over 5. But yes, you can play with this e and log relationship. You're saying what you have is a 37/5 times this log.
Yes.
Move it up as an exponent. 2 to the 37/5.
It might be easier.
Cancel your e and log, and that's what's sitting there, is a 2 to the 30. In other words, yes, this whole conglomeration of numbers is actually 2 to the 37/5. Is that what you just said?
Mm-hmm.
And you're right. All right, yeah, you're right. At some point, we don't have to play those games anymore. We'll pick up our calculator. We want a decimal version of these mice. Yeah. Anyway, how many are there?
125,640.
Really?
24.
Wow. Okay. It would have been a lot worse, I guess, without that cat, but cat did it for 37 years.
Cat's pretty dead, actually, right?
Or really bad.
Cat's even live for 30
We can't really for that long.
Yeah, right. We could worry about the cat populations beginning. So that's why they just have one cat, right? Otherwise, we could have the cat population would be growing at the same time,
And then more cats.
and then killing more mice. Oh my God.
That's a lot. That's a lot.
Killing 11 mice a day.
So this is just one really old cat. Oh, it averaged out to 11 mice per
About
day.
11 mice a day for 37 years.
Wow, that's a pretty good cat. Okay, that's a problem. That's a good problem. It's it's population growth with this extra little added sophistication of a piecewise scenario with a little death rate going on. Let's do a temperature problem. And if you don't mind, and I didn't do a temperature problem the other day, I want to make up a temperature problem. I'm going to just make up an example. Is that okay? We'll get rid of this, and let's do a temperature problem. And I guess I want to say that at 3 p.m. on February 4th, they found a dead body of a math professor.
Oh.
Found a dead body of a math professor in room 7112. That happens to be this room. And anyway, the first thing they did was take his temperature. His temperature, I mean, they were smart. smart bunch of people who, his temperature was 78 degrees Fahrenheit. And then they called the cops, and they roped the building off, you know, sealed everything, called the cops. The cops got there an hour later. They were busy, you know, cops were busy. Cops arrive 1 hour later, and they take his temperature. And the temperature now is 64 degrees Fahrenheit. See, maybe you understand what's going on here. Oh, and by the way, let's just say, you know, this room 7112 remains a constant. We're going to say it remains a constant 57 degrees Fahrenheit. That's the temperature of this room. Well, this is our model, and this was the differential equation. We already solved the differential equation in general for a surrounding medium constant temperature, and that's what we have. What is my surrounding medium temperature? 57 degrees, so that's this 57. So we can just use this model again. I don't really have to do any calculus or DE on this problem. It really turns into kind of an algebra problem using this model. What I like to do is kind of organize my data. You know, at some point I want to call time 0. And it's very convenient to call one of the given times 0. So we'll call that 3 p.m. 3 p.m. is 0. And what was his temperature? 78. Okay, here's another piece of data. 1 hour later, I guess, is that what it is? 1 hour later, the temperature was 64. The M is 57. And I still haven't asked you a question. Do you know what the question is?
When did he die?
Yeah. When did he die? Right. What was his time of death? Find his time of death, which was before 3 p.m. And maybe you realize that the strategy is this. When you're a human and you're healthy and you're alive, what is your temperature?
98.6.
98.6.
So we're assuming he didn't have like a cold.
Right, he didn't have a fever. Right, so he was 98.6, and then he died. And then he's in this cold environment, 57-degree environment, and his body begins to cool down at a rate proportional to the difference between the body and the surrounding medium. Newton's law of cooling. So the question above is, so before time 0, the answer is going to be some negative time. When did he die is the question. And in other words, find the time when his temperature was 98.6. But these two pieces of data are going to help you with your model. Your model has an M in it. We know what M is. But it also has two unknown constants, C and K. And that's sort of been the game already today. You can use this information to help you find C and K. Then you can answer any question anybody asks you, which is this question. I'm going to help you with that. Any questions? Have I described this problem okay? You guys okay? Maybe you've done one like this before. Let me just officially write the question down here. Find the time of death. All right, so like I said, it's algebra. Here we go. I'm going to plug in a 57 for this M. I'm also going to do something else. I'm going to take this first piece of information here and plug it in. So the temperature is 78. The M was a 57. You remember that. The C, I don't know C. I don't know K, but I'm about to plug in a 0 for T. So if you plug in a 0 for T, this is e to the 0. And it's a 1, and it's a C, and you subtract your 57, and C is You subtract this 57. I think I've seen people divide before. That's weird. You subtract this 57 and the answer is 21? 21. So C is 21. All right, now I'd like to find K. I'm going to move over here where I got a little more room. This piece of information will probably help me find K. Again, it's this model. I'm plugging in a 64 for the temperature. 64 for the temperature. M is 57. I just found, oops, equals 57. I just found C. What was C? 21. E to the K, and now I'm plugging in 1 hour, yeah, for time. I'm doing this in hours, I guess. 1 hour for that time. Cool, I can do a little algebra and find K. On your mark, get set, go. Subtract 57, you get 7, divide by 21, you get 1/3. Take the natural log of both sides. All right, so I did 3 steps in my head, and I think I got this answer. You can help me, see if I'm right. I did 3 steps in my head and got that answer, am I right?
Yeah.
Cool. That's K. Again, we could decimalize it, but I wouldn't want you to round it off, so I'm just going to leave it like that for a while here. What do I have? I got C, I got K, I got M. You know what? I have the model now. I have the temperature model for this scenario. His temperature at any time is 57 plus 21 e to the natural log of 1/3 times t. And I can ask a lot of cool questions now. After, when t is some certain time, what's his temperature? But what I'm really interested in is, when his temperature is 98.6, what was the time? And that'll be his time of death. How are you guys doing? Any questions? These 2 pieces of information helped me with my model. One of them helped me find C. The other piece helped me find K. M was given in the problem. M was this given. So I got my model. And here I go. 98.6 is his temperature. 57 plus 21 e to the natural log of 1/3 over times t. I got to solve for t. Takes a little bit of algebraic moves here. Subtract 57. 41.6. Divide by the 21. That equals this e to the log of 1/3 times t. I think I'll log both sides. The natural log of 41.6 over 21 equals, the log kills this e, it leaves me with this log times t. One more move. Divide by, no, divide, I'm trying to get t, divide by that natural log. So it's this natural log divided by this natural log. This is going to be awesome. I hope it's a negative time.
-0.62.
Negative 0.62.
Yeah,
Is that what you get, huh?
yeah, with a bunch more decimals if you want more.
Yeah, I don't need more really, maybe. I guess that's 0.62 of an hour. Boy, that's not very long. That was
36 minutes before they arrived.
negative 0.62 hours. Yeah, multiply by 60 and we'll turn it into minutes, right? Is that what we'll do? Multiply by 60, what is it? 30, what did you say?
37.
Yeah, 37.
37 minutes. We'll round it to 37
Oh,
minutes.
yeah. Before they arrived.
Before 3 o'clock. Well, that was before, yeah, before they found him at 3 o'clock. So when is that?
Maybe they
Two-
did.
2:23. 2:23 p.m. on February 12th. You know, luckily, I won't be here. We get out at 1:45. I'll be long gone,
Maybe the people that found them.
free and clear. Get one over on the old mathematics, right? Just cut plans a little early. Pull a fast one, save my life. I appreciate that. Are you guys okay? That was kind of fast. It was just algebra. It was this model. I like these questions, and you should like them too. They're fairly easy. Listen, these tougher problems are these tank problems. I'm going to do another one off this page, if you don't mind. This, I want to do this number 5. Yep, number 5, which actually kind of goes with number 6, to tell you the truth. This is tough and lengthy. We might be able to finish it before class is over here. This number 5. This is a tank problem. Mixing tank problems. I didn't outline that on the board here today, but we had a little preview of that last week. Here's what I do with these tank problems. They're written sort of in paragraph form, but when I read that paragraph and write it on the board, you'll see how I do it here. I do this. It says a 400-gallon capacity tank. All right, stop. So I draw this. A 400-gallon capacity tank. I make little notes. I say it's got a capacity of 400 gallons. You with me? I mean, I read the paragraph, but I sort of draw this picture. I think this is my suggestion how you should work. You can work wherever you want, but I have these suggestions. It says it initially contains 20 pounds of salt dissolved in 200 gallons of water. Okay, so it's got a capacity of 400 gallons, but initially it's only got, initially it has 200 gallons of water with how much salt? With 20 pounds of salt, I think it said.
20 pounds.
All right, these are the good ones. These are the good problems. I love these. All right. Now what happens? Sally begins to add a concentration of 3 pounds per gallon at the rate of 7 gallons a minute. Okay. She's adding. This is coming in 3 pounds per gallon at a rate of 7 gallons per minute. That's what's coming into this tank. It's a lot of salt. It's 3 pounds per gallon. First of all, that's a lot of salt. Then it's coming in at 7 gallons a minute. Anyway, it's a lot of salt. That's a big old tank. Anyway, the well-stirred mixture then is being removed from the tank, exits the tank at a rate of 3 gallons per minute. All right, listen, on these tank problems, that's it, by the way. That's the scenario. That's the picture. Now we gotta set up a DE. We gotta set up a differential equation. And I had some notes that said, well, we'll work on that. Hang on just a second. You know, with these tank problems, there's always 3 scenarios. Either the tank sort of remains at the same water level, or the tank is gaining water, or the tank is losing water. What's going on in this one? How much is it gaining?
4 gallons per minute.
Thank you very much. You're saying it's coming in at 7 gallons a minute, but it's only exiting at 3 gallons a minute. It's gaining 4 gallons a minute. So, by the way, I guess this thing will be full pretty soon. Hang on, let me just, yeah, you're right. Let's just think that through again. You're saying because of those 2 numbers, this thing is gaining 4 gallons a minute. And by the way, it's got to go from 200 to 400. It's got 200 gallons to be full. So when is it full? 50 minutes. 4 gallons a minute, 200 gallons to 50 minutes. Okay, so this thing is full when T is 50 minutes. Right, thank you. You know what? I'm sorry, but it's going to be full in 50 minutes. But I don't think anybody shuts anything off or anything. In fact, and there's no top on it. You know what I think? I think it just starts overflowing after that. And and then we might need to pay attention to that. What is this making you think of?
Piecewise.
Good, piecewise again. Right. I think we got a certain DE while it's filling, and then as it starts to overflow, something changes, and we got a second piece of the DE. You're right. So there's a DE for the first 50 minutes, and then a DE for the second, for after 50 minutes. Right. Here is the DE, by the way. It is, it's written for the amount of salt in the tank at any time. It's pounds of salt per time. A is pounds of salt. By the way, is there an initial condition on this one? A of 0? 20. It's the 20 pounds of salt. We're looking for the amount of salt, not the amount of water, really. But and then my notes said, well, here, I'll write my notes again. My notes said, I'll just write this here again. It said it's the concentration coming in multiplied by the flow rate coming in minus the concentration going out multiplied by the flow rate out. Flow rate out. Really, ultimately, that's rate in minus rate out. And my notes on the other page kind of say that. I think we've said that last week. But let's fill this stuff in, man. Here we go. dAdt is, now here we go. The concentration coming in. What's that? Concentration coming in.
21.
That's the 3. Actually, that concentration is just the 3. The 3 pounds per gallon. Concentration is pounds per gallon. Does that make sense?
Yeah.
Pounds per gallon. So that's the 3 pounds per gallon. And then the flow rate coming in is the 7 gallons per minute. It will be a 21 is what it'll be here. Minus the concentration going out. You know what, you guys? That's always sort of the tricky part. Let's skip past that a second. What about the flow rate going out? The flow rate going out? That's the 3 gallons per minute. By the way, if this is, the units on this is pounds per minute, and if we kept track of these units, we would see that we now have pounds per minute is what we have here. Pounds per minute. So this works, this jives. Here we go. The concentration coming out. All right. The concentration coming out. Well, concentration is an amount of salt over an amount of water. So the concentration that's coming out is actually an unknown amount of salt. So we're going to call that A, an unknown amount of salt A, over how much water is in the tank. And the water in the tank is constantly changing. We decided that we said that it's gaining 4 gallons a minute, but it started with 200, and it's gaining 4 gallons a minute. Can you write an equation for the amount of water in this tank? 200 plus 4T. Awesome. That's awesome. The unknown amount of salt and this changing amount of water in this tank. Yep. It's not that hard, right? Except now we're going to solve this DE. I will, listen, before I solve that DE though, I did describe, if I read a little further on this problem, number 6 says, I mean 5 has its own question, but number 6 says, find the amount of salt in the tank anytime after it starts to overflow. And we described how if we put these two problems together, then it's a piecewise problem is what it is. And so it is this until it fills up. So it's this when T is less than 50.
Yeah.
Okay. And then let's write the DE. What would it be after it starts to overflow? Let's check this out. You ready? After it starts, I got to imagine it's up there now. It's overflowing. Here we go. What's coming into the tank? That didn't change. I'm still bringing in 3 pounds per gallon at 7 gallons a minute. Even, I'm still bringing that in. And then I'm going to subtract the concentration leaving. What about the flow rate leaving? This is for T greater than 50 now. The flow rate leaving, thank you. You know, once this tank fills up, then it's sitting at 400 gallons and it's not changing. Now we're still losing 3 gallons out the bottom, but to keep it from not changing, then the water coming in, the amount coming in has to match the amount going out. So it's, he said this is a 7, is what he said. Because the amount coming in has to match the amount going out. It has to be. If it's sitting there remaining, it's remaining at 400 gallons. Now, you know, where it's coming out is really insignificant, but technically 3 gallons a minute are coming out the bottom. Apparently 4 gallons a minute are falling out the top. None of that matters too much. It's a well-mixed solution and we're losing 7 gallons per minute, right? But this is pretty cool because this is easier. Now, since it is remaining at the same level of 400 gallons now, the concentration in the tank is an unknown amount of salt over how much water? 400. It's not changing now. Right. This is a little bit easier DE than this one, but it's really one big piecewise DE is what it is. And I guess I should solve it. It's a big piecewise DE for this whole beautiful scenario, before and after it overflows. If I finish this problem, I'll have the amount of salt in the tank at any time, before and after overflow. I got an initial condition. It's a beautiful DE, piecewise DE with an initial condition. Let's do it. I mean, I like doing it. But it's more fun to talk all about the problem, talk all about the concepts. Now, at some point, you got to get down and do some math. And that top DE is let's work on that. So I'm going to go over here and I'm working on these. I'm working on them in 2 different pieces. I'm not going to try to do them both at the same time. 2 different DEs in a way. And so I'm starting with that top piece. And it's dA dt. You know what I'm going to do is I'm going to move this term over, you guys. It's negative 3a. I'm going to move it to the other side. So it'll be a positive 3a over 200 plus 4t. Equals 21, I think. Is that kind of how this plays out, right? Move this to the other side, it equals 21. And you need to probably find your integrating factor. Wait till you see this. The integrating factor is e to the integral of 3 over 200 plus 4t. Good luck. That is e to the 3 ln of 200 plus 4t. But there's a detail in there you got to catch. Thank you. Technically, for this to be an ln, you did a little u substitution on the 200 plus 4t. If you did a little u substitution on the 200 plus 4t, then what was du? 4 dt. So the result of that is it spits out a 1/4. So this is a 3/4 here, ln of 200 plus 4t. Hey, I'm going to take that 3/4 and move it up top so it's an exponent. Then I'll cancel the e and the log. So what is my integrating factor? 200 plus 4t raised to the 3/4. That's my lovely integrating factor. What do I do with that integrating factor? Multiply through by the DE. Okay, now wait a minute. There's the DE. After I multiply through by the DE, my left-hand side is the product rule derivative of the integrating factor times A equals the other side. What's the other side? A 21 times the integrating factor. Actually, you're right. I got to remember. Right. I got that set up. Now I integrate, and the next step I'll have a plus C. Right. I'll integrate now. 200 plus 4t to the 3/4 times A equals. Integrate this. I'm doing this in my head, you guys. I like to take some shortcuts since we're finally in differential equations. I don't like to write out all my steps here. What I'm doing is a little u substitution on this. And so it's u to the 3/4. How do you do a u to the 3/4? How do you integrate a u to the 3/4?
4 over 7.
You add 1 to it, so it's 7/4. It's 7/4. Then you have to divide by 7/4 or multiply by 4/7. There's a 21 out there. And then something else happened. Since you called this u,
It's to spit out a 1/4.
it spit out a 1/4. So I did all that integration in my head, if you don't mind. The u substitution spit out the 1/4. The 4/7 is the part of the integration, and the 21 was already out there, plus c.
C1.
Yeah, we better call it C1. Good idea. All right, I'm running out of room. You know what? I'm going to go back and erase this middle piece here. Invest in some paper this semester. That might be a good idea. Here we go. Oh, hey, what do I do now? Divide by this and I'm done. Divide by this and you're done. You get A equals... And what's fun is you're dividing by 200 plus 4t to the 3/4, and you're dividing by that under here, which is 200 plus 4t to the 7/4. By the way, out front here, what's out front here? A 3. A 3 is out front here, and then you get 200 plus 4t to the 1? To the 1. I love that. Plus C1, 200 plus 4t to the negative 3/4. You could say it's divided by 200 plus 4t to the 3/4. This works here. Divided by that. C1 divided by that. That's awesome, you guys. My initial condition should help me find that C1. My initial condition should help me find C1. I'm doing it. You plug in a 0, you should get 20. If I plug in a 0, this is a 600. You guys agree? Plug in a 0, 600?
Yes.
And plug in a 0 over there, and you get C1 over 200 to the 3/4. So I'm going to subtract the 600. It's negative 580. It equals C1 over 200 to the 3/4. To get C1, you have to multiply by that 200 to the 3/4. And so C1 is, I would like that decimalized, but here it is undecimalized. Negative 580 times 200 to the 3/4. If you can decimalize it for me, I'd appreciate it.
Negative 10.91. Oh, wait.
I got negative 2,127.31835.
2,127.
Do you want all the decimals?
Just give me one.
All right, 0.3.
0.3.
Excellent. Right back. Yeah, you got it right.
Divided by 600? So don't divide it. Yeah. Subtract 600.
Oh, okay, wait.
That's not what I got. Yeah.
Okay. I subtracted by 6,
Yeah.
not 600.
Yeah.
Oh, okay.
All right.
Subtract
I got it.
600 and multiply by, all right.
My bad.
That's all right.
Negative
30.
308 46.1.
Wow.
Yeah.
30,846.1. That's our C1. Thank you. All right, this is a lot of work. I like to, I like to rush through it, but I also like to relax and enjoy the work. So, so what do we got going on here? We got the answer for the first 50 minutes. For the first 50 minutes, we have a real live, legit answer here. Sorry. Yep, that's it for t less than or equal to 50. I guess I got to solve the other piece. And I erased it. Maybe you could help me remember what it was. It was, the other piece was dA dt equal 21 minus
A over 400.
times 7.
Times 7.
Yeah, A over 400 times 7. Okay. So this was my second piece, and this should be a little easier DE, but it's still got its own challenges. I'm going to move this over to this side and do my integrating factor method again. What I have then is dA dt plus 7a over 400 equals 21. What's the integrating factor? E to the integral of 7 over 400. So what is that? E to the 7 over 400 t.
Oh. There's a whole decimal for that if you want it. Not
Oh yeah, a point something.
0.0175.
0.175.
If you want it.
I don't know, I might need it later, thank you.
Yep.
What do I do with that? Multiply through by it. After I multiply through by it, this right-hand side becomes, the left-hand side becomes the integrating factor times A. On the right-hand side, I get 21 times e to the 7 over 400 t. Yeah, I multiply through by the integrating factor. It shows up. It shows up on this side, but then that's automatically that product rule, so I automatically do that, and then it shows up on the other side. Then I integrate both sides. On this side, it's e to the 7 over 400 t times a, capital A, and it equals the integral of that. You guys know when you integrate e to the 7 400ths t, it spits out 400 over 7. If it spits out 400 over 7
Times 21. It's
times 21,
1200.
it's 1200. Thank you. 1200 e to the 7 over 400 t plus C2. Man, I'm so close. This A is now 1200 plus C2 e to the negative 7 over 400 t. I'm so happy. But I got to find that C2, I guess. How do I find that C2?
Set an equal.
Oh, set that top piece of the DE, set equal to the second piece of the DE at t equals 50. You're right. I'm going to try to do that right here. At t equals 50, at excuse me, t equals 50, I would plug 50 in here. Hey, that's 200, that's 400 times 3, that's 1200. I'm plugging 50 in there. That's negative 30,846.1 over 400 to the 3/4. We're going to decimalize this stuff in a minute. And it equals, plug in a 50 right here, which is 1200 C2 E to the, when you plug a 50 in there, you can do whatever you want, but it looks like, to me, it looks like a negative 7/8 now when I plug a 50 in there. 50 over 400 is an 8, or 1/8. Hey, these 1200s cancel. If you want C2, you can multiply by e to the 7/8. C2 is that nasty number times e to the 7/8, which I would like you to decimalize for me again, please. What is that?
You got negative 827.3.
All right, we need confirmation. We always need confirmation. We don't have confirmation.
I got, yeah, that's right.
Two mistakes.
I mean, this is not the most trivial calculator use here, but it is calculator use. But you're right. You need this 3/4. You know, putting that 3/4 in parentheses might help, or whatever. We think that's it?
Yeah,
That's it.
Thank you. We're done. We are finished. The answer to this DE is in 2 pieces, and there's the amount of salt in the tank before T equals 50, and after T equals 50, we have this answer. 1200 plus C2, which is negative 827.3 e to the negative 7 over 400 T. Answer to the DE, complete and utter answer. Wow, that's pretty cool stuff. I mean, I can sit here and ask you a bunch of questions now. How much salt's in the tank in 30 minutes? You plug into 30. Of course, you plug into 30 up here, right? Here's a good question, though. Here's the best question. What is the limiting amount of salt in this tank? Or if we let this thing run forever, just overflow and run forever, in other words, what is the limiting amount of salt in this tank? That's a fancy way of saying, let T go to infinity and tell me the amount of salt, please. I mean, let's let this thing run forever. If we let T go to infinity, of course, that's past 50. You think infinity is past 50? A little bit. That's hard to say, actually. Infinity is past 50. And, right, we would go down here to this equation and let T go to infinity. And, of course, when T goes to infinity, this e to the negative infinity goes to 0. This whole term goes to 0. What is the limiting amount of salt in this tank? 1,200 pounds. 1,200 pounds. If I wanted to, sketching a graph of this would be, sketching a graph would be kind of fun. You know, it's a little tricky. I'm not at all sure what this looks like, but your graphing calculator could help you. But let me just say that we started at 20, and we're gaining. I'm not sure what kind of concavity we have. I'm not sure if I'm drawing this right, but I know one thing. At 50 minutes, what we did is we ran into a new function. And by setting these equal, you know, we made this thing continuous. So we made this second piece match the first piece at T equals 50. We did. And so the second piece is here now, but it is approaching an asymptote. And what did we say the asymptote was? 1,200 pounds of salt. Yep. So the picture looks something like this. 2 pieces, they are connected at 50. because it is, we made it a continuous function, but then eventually it's approaching 1200. You want to see something kind of funny? I could have, we did, I want you doing differential equations and solving differential equations and doing all this work. That's what we got to do. But if I would have asked you about an hour ago, before we started this, if I would have asked you, what is the limiting amount of salt in this tank? Or as t goes to infinity, how much salt's going to be in this tank? You could have used a little logic. You could have said, right now it's got a very weak concentration. It's 20 pounds in 200 gallons of water. What is that concentration? It's 20 pounds in 200 gallons of water. It's 0.1 pounds per gallon. Anyway, what's coming in is pretty concentrated stuff. It's 3 pounds per gallon. So it's becoming more concentrated as we go. But the incoming concentration sort of dictates the whole thing. We can never get higher than the incoming concentration. So eventually, the well-stirred mixture gets drained, but it's gaining concentration, but the most concentrated it ever gets is the incoming concentration, 3 pounds per gallon. It's a 400-gallon tank. It's going to be full of water, 400 gallons, 3 pounds per gallon. We're going to have 1,200 pounds of salt in the tank. So luckily it works out that way. Luckily the math works. All right, you guys should work on some of this. I'm going to quit.